Hello, this is the second video in a series of 4 to help with revision for Chemistry Paper 1. Again, for all students, foundation and higher, and where there are higher parts, I'll make sure that I indicate that. So this second part then is all about bonding, structures and properties of matter. And we're going to have a look at each different section. Again, if you want to stop the video at any time and create your mind map, you can. Or if you just want to listen for your key facts to learn, then that's great. So we're going to start off then by looking at states of matter. Okay, so if we move over to this section of the presentation, so states of matter. First of all, straightforward, states of matter, you've got solid, liquid and gas. And if you're asked to describe what they look like, then the solids vibrate around a fixed position. They are in very neat rows, all touching each other and quite tightly packed. Liquids are random, they are close together but they do flow. And a gas, again, very random but also this time very quick. There's a lot of kinetic energy. The other symbol you need to make sure you're aware of is AQ, aqueous. Aqueous is a solution which means that it's dissolved in water. Now, one of the things you need to make sure you know is that every single pure substance has got its own melting point and boiling point, and that's how we tell if a chemical is pure. And so I always think about water because that's an easy one to think about to start with. So I can remember what the melting point is and what the boiling point is, because then you could apply this to any different chemical. So if you've got a solid, to go from a solid to a liquid, that's the melting point. And if you go from a liquid to a gas, that's the boiling point. So with water, ice turns to water at 0 degrees, that's the melting point, and water to steam at 100 degrees, and that's the boiling point. I could now take any of these chemicals in this table here, and it is very often a question that says, what is the state of each element at 25 degrees room temperature? Which is room temperature. Now, if I looked at fluorine, for instance, fluorine's melting point is minus 220. So if I put fluorine there, and I say the melting point there is minus 220, and the boiling point here is minus 188, well, room temperature is 25. 25 is up here off the table. So that means that this fluorine then would be a gas at room temperature. If I look down here, for instance, bromine is minus 7 melting point, so it goes from a solid to a liquid there, minus 7, and its boiling point is 59. So that goes from there to there. So 25 actually appears between the two. So 25 tells me that bromine would be a liquid at room temperature. So like I say, if you draw this out first and then put your chemicals into this, you will see it's much easier to picture what's what. Now, if I have a look then, there are different types of bonding that you need to be aware of, okay? And the first one we're going to have a look at is ionic bonding. Because ionic bonding, there's 3 types of bonding that you need to be aware of. There's ionic, there's covalent, and there's metallic, okay? And ionic is between a metal and a non-metal. And over here you've got the rules. It's between a metal and a non-metal. Remember, your metals are on the left-hand side of your periodic table, non-metals are on the right-hand side. It's all about electrons being transferred. It's not about sharing at all. That is covalent bonding. You must not use that word. It's about electrons being transferred from one chemical to another. Usually it's metals that are losing electrons and non-metals that are gaining electrons. And then, most importantly, the particles become charged. And they become charged because originally, if they've got 12 protons, which are positive, and 12 electrons, that means it balances out. If you lose an electron from there, you lose a negative. That means you've got one more positive. So your particle will become charged. A little bit like this example here. So, for instance, if I've got sodium chloride, which is the salt that you put on your chips, the sodium ion will become charged as positive because it's given away one of its negatives. It's got one more positive proton. whereas chloride ion has gained an electron and so has gained a negative, and that's what we say, it's gained a negative. Please remember to do your dot cross diagrams, crosses for one atom or ion, atom before, ion after, and it's gained one electron. This one here, you can see magnesium oxide. Magnesium has given 2 electrons away, so it's become 2 positive, whereas this oxygen has received 2, so it's become 2 negative. It's received 2 negatives. Now, this example here is probably the hardest one you're going to come across, and that's Na2O, and that's because you've got 2 sodiums and you've got 1 oxygen. Each of the sodiums is in group 1, so they will give 1 electron away each, but oxygen will receive 2, so we can say that these have become positive because they've given 1 away each and they've got 1 more proton, whereas this has gained 2 negatives, so it becomes 2 negative. That's about as hard as I've seen with ionic bonding, but there is a very good chance you will be asked to draw one. In terms of properties, the giant ionic structures have strong forces of attraction. They generally have high melting points and boiling points because of this. They do not conduct electricity when they are solid. So if you think about salt does not conduct electricity when solid, but if you make them molten or in a solution, then they will conduct electricity. Okay, let's have a look over at covalent bonding then. So you can see everything in orange here is to do with covalent bonding. So let's start off by looking at the rules. So the rules this time, and I can see I've made a mistake there, naughty me. The rules are between 2 non-metals, okay? It's a non-metal and a non-metal, okay? They share electrons. The bonds are strong. Some are small molecules, so water, H2O, and carbon dioxide. In terms of examples, generally, if you look, you can see there's no brackets here. It's all about sharing the electrons. So here I've got water, H2, I've got 2 hydrogens, 1 oxygen. Hydrogen has got 1 electron in its outer shell, oxygen has got 6. So all I've done there is I've represented the electrons as crosses for oxygen and dots for hydrogen. Now, the first shell needs to be filled up with 2 electrons. So if I join that hydrogen on to there, I can share that electron from oxygen, and I can share this electron from hydrogen. That fills up that shell, and then if I do the same on the other side, these 2 here then join up to make a full outer shell of 8 for oxygen. So that's water, and that's why they don't tend to conduct electricity. Carbon dioxide is a little bit more difficult because this time oxygen needs 2 to fill it up, and the carbon only had 4 in the first place, so it needed 4 to fill it up. So you can see we've got a double bond going on here, and we represent that with 2 lines. You can see with water it was only 1 line because it was just sharing 1 bond. With carbon dioxide there's 2 because it's sharing 2. So oxygen has shared 2 here, carbon has shared 2 here, and then we've got a double bond. But if you count, 1, 2, 3, 4, 5, 6, 7, 8, full outer shell on all of them. The third type you'll get with covalent bonding is this one, and this is CH4, methane. So carbon again has got 4, but it needs 4 to fill it up. Well, luckily we've got 4 hydrogens that have all got 1 each that they want to share. So if we share all of these, then you can see that carbon has now got 8, the hydrogens have all got 2, so they're all very happy. But this time we represent that bond just looking like that. In terms of small molecules, generally covalent bonds are small molecules that do not conduct electricity. Because they're small, they only have a low melting point and boiling point, as they have weak intermolecular forces. Whereas if we look at some of the giant structures, we're looking at, generally, these first 2 here are made of carbons, okay? So diamond has got 4 strong carbon bonds. It's hard, it's shiny, but it does not conduct electricity because it does not have any free electrons. Whereas graphite's the one that you see in layers. and it's got really strong covalent bonds in the layers of carbons. However, between the layers has weak intermolecular forces, and that's why if I take a pencil that's got graphite in it, when I put the pencil down onto a piece of paper, I can easily move it along and leave a layer of pencil, because I can easily break the intermolecular forces between the layers and leave some on the paper. And we say that it's very slippery. The other one that you might come across is silicon dioxide, and that's to do with oxygens and silicons being joined together. So oxygens will join together with 2 silicons, and silicons will join together with 4 oxygens. Okay, so let's have a look then at fullerenes. Again, fullerenes, we are looking at special metals and materials. Before I go on to the fullerenes, we're just going to look at graphene, because we've just looked at graphite. Graphene is a single layer of graphite, and this is becoming a really important chemical at the moment, because scientists are discovering lots of uses for it, because it's very strong, it's a good conductor, and it's near enough transparent. So that scientists, if you do some research, are finding lots of new uses for graphene, and it's a really exciting material at the moment for scientists. If I looked at fullerenes then, fullerenes, again, we're looking at carbon as a fullerene. So Mr. Buckminster and Mr. Fullerene first discovered that if you had 60 carbon particles in the shape of a football, that's called Buckminster fullerene. And it's quite exciting, because they're now starting to look at these as developing into nanotubes. And some of the things that they're doing with that is they're starting to look at delivering drugs in the body in these nanotubes to the place where they're needed, and then to release them rather than just travelling all around the body. You're also looking to use them as lubricants to make so there's less friction, so less energy is lost, catalysts, and then also things like reinforcing tennis rackets to make them even stronger. If we look over here at polymers, now this I am going to mention again when I get to paper 2 and look at the development of crude oil into plastics. But polymers are essentially, we are looking at plastics, it's covalent bonds, and it's this process of additional polymerisation. Now the sort of thing you might be asked is, they may give you a formula that looks like this, and it's generally an alkene, and you can tell that because it's got a double bond in there. If I break that double bond and make those hydrogens stand up, that bond then is ready to attach onto another chemical. So by doing that, from taking that to that becomes a monomer. Mono means one, so I've now got one building block of plastic. So this particular one is ethene, okay? If I put lots of ethenes together, I get polyethene, which is plastic bags. You can do the same things with polyester, polystyrene, polyvinyl acetate, which is PVA glue. That's how these are made. You take an alkene, and with a high pressure and a catalyst, you make a monomer. You take them building blocks and build them together, and you make a polymer, because poly means more than one. They may ask you to work out the formula from a polymer. Just look at the repeating pattern and just draw one of the repeating patterns. Make sure you put it in a bracket with a little n, because that means you can add lots of them together. Metallic bonding. Now this is a question the exam board absolutely loves, is to get you to draw a metallic bond. Make sure you draw positive ions. It's a solid, so it's all nice and neat rows, but you have 3 delocalised electrons, and that's why metals actually conduct, because they've got these electrons that can carry the charge. And the last thing to mention is alloys. Alloys are a mixture of a metal and another metal, and the reason that we do that is because it makes it much stronger and harder than a pure substance. So we can mix lots of different things together. So for instance, steel is made of carbon and iron, hence the reason steel rusts, because the iron oxidises. So alloys are actually quite useful. Okay, that's the end of part 2. Make sure you watch parts 3 and 4 to get your full revision for paper 1.